Good morning, students. Welcome to the next session of structural analysis 2. So in the previous class we have started our explanation of moment distribution method. There we have calculated stiffness of the members when a member is being subjected to a clockwise couple at one end and the other end of that particular member is being fixed. What is the stiffness of the component? And then we have taken another member which is having a clockwise couple at one end or the moment at one end and the other end is being hinged. In these two conditions, we have calculated how the response or how the stiffness of the member, and also we have calculated what are the rotations occurring at the location of the moment. Okay, so at B point when I am providing M moment, so at that B, what is the rotation or what is the slope of that particular segment? Again, for the segment AB, for the condition of fixed end at farther end and hinged end at the farther end, also we have calculated the stiffness. In today's class, we are going into a new term which is distribution theorem. There we have learned carryover theorem, right? So those carryover theorem and carryover moment, there we have learned. Now it is the distribution theorem. See what it is meant by distribution theorem. A moment which is being applied to a structural joint to produce a rotation without translation. For explaining this distribution theorem, distribution means what? In the sense itself, it is distributing something in the form of a moment, in the form of a rotation or in the form of any other thing. When I am applying something, it is distributing to all the members. Further, we are taking a consideration. Later, we are explaining how the distribution theorem applies. Okay? A moment which is being applied to a structural joint produce rotation without translation. Here I am providing any moment for producing rotations only, not to the translations. Translation means horizontal changes. Rotation means this body is being taking this curved shape with the horizontal. This slope generation I am thinking. Okay, not the horizontal displacement. That is translation, transport, moving. Okay, but here rotating, being in the same place, but the member is having some rotation in that body. Okay, and without translation gets distributed among the connecting members at the joint in the same proportion as their stiffness. So what it is saying, when we apply a moment to a joint, so joint may be a joint between two beams, maybe some first segment and the second segment. In this way, some continuity was there. In this condition, at this joint, if when I am producing some moment which is causing rotation but not causing any translation, okay, I am subjecting this. Now, what happens? The moment is getting distributed. If we produce M moment, that M moment is being distributed among the connecting members. Okay, how many connecting members were there? Those connecting members, this total applied moment will be distributed. How? Based on which reference they will get the distribution. So, if any work has done, how we will distribute? This person has done more work, this person has done less work. Like that, we will distribute the money. Like that, here also, based on their stiffness parameter. Based on the stiffness parameter of the member, the moment will be distributed among the members which are being connected at a joint. So, at a joint, when I am distributing the moments, those moment distribution will be according to the stiffness and also based on the proportion of the stiffness. If the first member is lesser stiff than the right one, so the lesser stiff proportion member will take lesser moment than the right one moment. Okay. Why all these things happening? Because at a joint, the slope on the left side or on the right side or every segment will show the same rotation or the same slope. So, for providing the same rotation or same slope, this segment which is being flexible means it is having lesser stiffness. When a member having a lesser stiffness will take lesser moment to produce the same rotation, while the member which is having more stiffness will take more moment for producing the same amount of rotation. That's why How? The stiffness is there based on the stiffness proportion. As per the same stiffness proportions itself, the moment will be distributed in the ratio. If 1:2, 2:3, like that, it will be distributed. You will go into the derivation, then you can get the clarity. Now, for that clarity, I am taking an example. Simply, we are connecting members AO, BO, CO, DO and EO, which are being connected rigidly. Rigid connection I am maintaining at the joint O. Okay, further I am taking the picture. See here, you can observe A, B, C, D and E joints which are being connected at joint O. Okay, now these members were connected like this. Again, how the structure is there, we will explain in the next steps. When you observe the picture itself, you can see at A, I am observing a fixed end. At B, I am observing a hinged end. At C, another fixed end. At D, hinged, and at E, another fixed end. Just for the complete clarity, whatever is the combination, we are taking an example involving all the types of farther ends. Okay, either maybe a hinged end or maybe a fixed end. These two combinations I am taking again at the same time for getting the clarity in the distribution theorem, how they will be distributed based on the segment, based on the support and based on the stiffness of the particular member. Involving all these three members I am considering. Now let capital M be the applied moment which is being applied at joint O. As we have already mentioned, all the members are being connected at O which is being very rigid, and at the joint O I am applying a moment M. Now the members are connected rigidly at O and the slope at O is same for each member. Just now only we have mentioned what we have said. When I am connecting many members like this, okay, maybe at some point, and I am applying a moment capital M. These members may have any type of joint, maybe a hinged, maybe a fixed or anything, whatever it is, but each member will show same rotation. Rotation means slope, in the form of slope. As this M is causing like this member may have movement like this. Okay, this member may have the elastic curve shape like this. And for this member you can observe some curve shape like this. And this member may have some shape like this. And this member, which may be a hinged, it may have some. Each member will show the same slope at the rigid joint. Each member will show the same slope at the rigid joint. So, as I am calculating the slope, the first slope, and for this segment, what is the slope, and for this segment, what is the slope value, and for this segment, what is the slope value. All these slopes are same that they are mentioning in the theorem. Okay, so let M be applied at joint O. Since the members are connected very rigid to joint O, the slope at O for each member, however is the length of the member, however is the condition of that particular segment, but the slope of that particular member at the joint O will be equal. Okay, so each member will show the same slope. See here, when it is fixed, you have observed some curved shape, but at the fixed end, zero slope. But for the hinge, you can give a smooth curve. Again, at the fixed, we should show some zero. Okay, at the fixed, there is no slope. Again, for the hinge, simply a smooth curve connecting those 2 points. Again, for the fixed, some zero indication and connecting the value. Here, you can see the slope of this particular member as some theta 1. Maybe for this segment, it may be some theta 2. Or it may be some theta 3. And as the member itself is having some name, that's why this theta 1 I can indicate as IOA. Slope of this OA member, and then slope of this OB member. In this way, each member is having some slope values, rotation values, and all these values were equal as per the theorem. Okay, and also each member will take some moment as I am applying the whole. I have given this total moment as M. So, how much they can take. Then, how much they will take based on their stiffness proportionally they will take. Let L1, L2, L3, L4 and L5 be the lengths of the members AO, BO, CO and DO. Either you can write OA, OB like this also. And also I1, I2, moment of inertia of each segment. I am giving everything is different. I am not at all considering the length of the segment is same, moment of inertia are same. No, every member can have its own properties such as Young's modulus, moment of inertia and lengths also. So each member is having different nature of length. Each member may have different moment of inertia. Each member connected there may have different Young's modulus. Okay, whatever is the combination, and I am observing different support conditions also. In all these situations, each member has shown some slopes IOA, IOB, IOC. In this way, we have given the slope at O point. Why at O? Because the first corner will indicate at the location and the other will indicate towards. I slope at O towards A, slope at O towards B. In this way, the slope calculation, the first will indicate at. Even we have given for the slope deflection equations also, where MAB, MBA. How we will write? M at A towards B, M at B towards A. In this way we will write, right? So the first term will indicate at which, and the next term will indicate towards. So at O towards A, at O towards B. In this way we have given the slope answers also. And then like the applied moment capital M is being divided into M1, M2, M3, M4 and M5. So the total moment I am giving, and each member is taking some quantity of the moment for giving the rotation. So those quantities I have taken them as M1 to M5, and each member, as we have already said, I have given the total moment. Then all these summation of the moments should be equal to the capital M, right? So M1 plus M2 plus M3, summation of all these moments should be equal to the total applied moment we are giving on the rigid joint. And also we can say IOA. These slopes we have already calculated in the previous class. Before entering into stiffness of the particular member, we have given slope of the particular member due to the application of M moment. A member which is fixed at the farther end and it is being subjected to maybe some support like this. So if it is being subjected to a moment M like this, and for this member when we observe the slope, okay, this theta, what is the value of this theta? The theta or the rotation when the farther end is fixed and a clockwise couple of M is applied at the nearer end. Now at the nearer end, what is the slope? That is equal to M L by 4EI. ML by 4EI. If in case of this combination was when the farther end is hinged and this support is having like this, then you can see this theta is equal to M L divided by 3EI. When the farther end is fixed, it will be divided with 4. When the farther end is hinged, it will be divided with 3. Okay, so you can remember like these two conditions. Here I am writing those terms only. When the farther end is fixed, nothing but for the OA segment. So IOA is equal to what is the moment taken by OA member? That OA member is taking M1 moment. If it is OA member, okay, so it is O and it is A as it is being fixed. So and it is taking a moment as M1 being length L1 having cross moment of inertia I1 and Young's modulus E1. So these things we have already known. Now what is the slope at this O joint due to the application of M1 moment? That is equal to IOA is equal to M1 into L1 by 4E1 into I1. So as why it has came? Because I have taken A as fixed. Maybe if joint B is hinged, how it will come? Using this condition, as this one is O and this joint is B as it is hinged, and due to this application M2 and the length as L2, Young's modulus is E2, moment of inertia is I2. So for this member OB or BO member, and it is being subjected to a moment of M2 at O. As we have given the total M, each segment has taken some moment. So I am taking that portion of moment only on the beam. I am taking that portion of moment acting on the particular segment. Okay. So whether it is a beam or a column, maybe in case of a jointed in the frame, maybe it may be a column also. Okay. Here I am taking a member at the joint O or at this corner O. I am applying a moment M2. Due to that M2, I am observing some slope at that location of the moment only. So that answer we have got as M2 L2 3 E2 I2, as the hinged end is there at the B. And then again at C, what it is there? And the next point, C is having fixed end. A is fixed, B hinged, C fixed in the way. Alternately D is hinged and E is fixed. And for the next end, which is fixed. Fixed, hinge, fixed. In this way we have given in the picture, right? So again, denominator by 4. M3, L3, 4, E3, I3, which is due to C is being fixed. Even though I am applying at the rigid joint, but the farther end is being fixed, I have got the slope like this. Even though this joint D is being hinged, I have got the slope as M4 L4 by 3 E4 I4. And then for the last joint, nothing but the E, as being E joint is being fixed. So we have got MOE is equal to M5 L5 by 4 E5 I5. So in this way we have calculated slope of each member at the joint due to the application of total M. That total M is being distributed to 5 parts, and those 5 parts has given individual answers. Okay. Now we have mentioned the slopes are being equal whatever is the length, whatever is the moment of inertia, whatever is the support condition at the farther end. At the joint O, each member will show same slopes or same rotations only. That IOA, IOB, IOC, all these slope values at the joint O are equal, and the ratios, just now we have calculated all the things, right? So the values of all these will be equal. So I have taken that part only. Keeping moments only on the top and taking the remaining thing in the denominator, we will see M1 by 4 E1 I1 by L1. So coming in the denominator. In this way we have got the next term. And finally, what is this term? 4EI by L. We have already calculated it as the stiffness of the particular member. 4EI by L. When the farther end is being fixed, the stiffness of the particular member will be sigma, or here I can indicate as sigma or any other notation, so I am indicating as sigma. Okay, so M1 by sigma 1, M2 by sigma 2. What these sigmas are indicating? Stiffness of the particular member as fixed end. So sigma. And as B is hinged 3, as C is fixed 4, again hinged due to 3, and again fixed 4. So in this way we have got stiffnesses of the members. Now equating the slopes, I have got the ratio between moment and stiffness, but I have equated slopes only. And we can say when I am applying the total moment, it will be distributed to all the parts. So capital M is equal to M1 plus M2 plus M3, which is nothing but the total applied moment. And also sigma. This sigma is equal to total stiffness of the joint at O. So the stiffness of the joint at O is equal to stiffness of the each member. So stiffness of each member will be equal to summation of all these stiffnesses will be equal to overall stiffness of the joint O. So see here, we have set sigma as the total stiffness at the joint. Just to take a simple example, when I am connecting a simple pole or a rod like this, okay, where I am giving some twist or couple or some movement onto this rod, but I am stopping every segment when I am connecting something like this. So this end I have connected, and I am trying to give some rotation. How happens? Because as the connection was there, they will show some resistance. So that resistance to the rotation due to the application of some moment is called as stiffness, right? So, if I increase more number of connections, okay, when we increase more number of connections to this and still we want to rotate, okay, due to this rotation what happens? Now I need to observe more stiffness because it is being connected by more number of members and it is showing more stiffness. How it comes? Because each member is showing some stiffness. So all these stiffnesses in summation will cause the total stiffness at the joint. Okay. So how I can say the joint O is showing some stiffness which is summation of the stiffness offered by each member. So this OA, OB, OC. So all these members are showing some stiffness. Now I am applying M moment involving all these stiffnesses only. This will show the rotation. Okay. So the overall stiffness at the joint O is summation of the stiffness of the each member. Now this M1. See here, just now we have got a ratio. M1 by sigma 1, M2 by sigma 2, M3 by sigma 3 in all is equal to capital M by sigma. This capital M is total moment we are applying. This sigma is total stiffness we are observing in the rigid joint. Now, taking this first and the last terms, M1 sigma 1 by sigma is equal to M. As we have got M1 by sigma 1 is equal to M by sigma. With this arrangement, I have got M1 is equal to sigma 1 by sigma times M. M2 is equal to sigma 2 by sigma times M. So, in this way, sigma 3 by sigma times M, sigma 4 by sigma times M and sigma 5 by sigma times M. Now, the ratio sigma 1 by sigma is called as distribution factor. So, the ratio of stiffness of the particular member divided by stiffness of the all the members at the joint. So, ratio of stiffness of the particular member. Maybe some member is showing some stiffness as 3E1I1 by L1. Okay. Maybe, just for example, maybe if you want, you can write as 4 also. As first member is having 4. So, this is the stiffness of the particular first member only. Now, divided by stiffness of all the members in a summation. Stiffness of the particular member by stiffness of all the members at the joint. The ratio of this can be called as distribution factor. Okay. And for the member OA. Okay. Towards the member O, towards A, that will be the distribution factor. And towards B, the corresponding stiffness we need to write. In this way, each member's stiffness will come in the top and the total stiffness at the joint will come in the bottom. The ratio of these two can be called as distribution factor. Similarly, sigma 2 by sigma, sigma 3 by sigma, sigma 4 by sigma, and all these are distribution factors for the members OB, OC, OD and OE which are being connected at O. The distribution factor for a member at a joint is the ratio of stiffness of the member to the total stiffness of the all the members. So, distribution factor means the ratio of stiffness of the particular member. Okay. Distribution factor for that particular member is equal to. So, distribution factor for the member OA is equal to stiffness of the member OA divided by total stiffness of all the members at the joint. Okay. Meeting at the joint. Maybe if you see a simple beam which is being continuous. Okay. As we have already mentioned, this may be our structure. So, this one is B and here some other thing is there. Now, you can see B, A member can have some stiffness. Due to it is being fixed 4 E I by L which is for the segment BA I am writing. Divided by the total stiffness of the two members. The first member stiffness and the second member stiffness. So, 4 EI by L of BA plus 3 EI by L of BC maybe it is C. Why it is 3? Because from the rotating point, at this point, why I am taking at B, okay, at B towards A, at B towards C, because I am calculating joint moments here. We are calculating the joint moments. So, once the joint moments have enough answers, we can go into the basic steps. So, I am concentrating at the joint. So, at B towards A, what is the distribution factor? At B towards C, what is the distribution factor? So, at means B. The farther end is the remaining end. As the farther end is being fixed, the corresponding stiffness is 4EI by L. As the farther end is being simply supported or a hinged end, it can be indicated as 3EI by L, and it shows the lesser stiffness than this fixed end stiffness. As the member is having fixity, it will show more stiffness. As this is having the hinged type, simply supported condition, the member it will give some lesser stiffness. We have already evaluated, right? So, stiffness of the particular member by stiffness of the total members which are being connected at the joint. So, that is the definition for the distribution factor. Now, the term relative stiffness, this may not be so much useful but will be useful for generating a tabular form. Okay. Further, again I am taking the same example. Relative stiffness calculation. Consider the rigid joint O where the members AO, BO, CO, DO and EO are being rigidly connected at the joint O, as we have already shown in the figure. Now, you can observe this picture. Just now only we have mentioned as it is being fixed. Maybe for some other example, the member is like this. So, the main members were AB, A to O joint and O to B, O to C and O to D. In this way we have given, and for this structure I am applying a moment of capital M in the clockwise direction. Due to the application of moment, what we have said, the total moment will be distributed among them. And what is the distribution theorem? The moment distribution will be, distribution of those moments will be according to their stiffnesses. So, according to their stiffness proportion only these moments will distribute. And also we have taken one more condition, that is slopes will be equal at the rigid joint. The slopes which are being generated will be equal at the rigid joint. Whatever is the condition, whatever is the length of the segment, whatever is the moment of inertia and whatever is the cross section, this slope values for each members will be equal. When we separate it like this, you can observe this picture and how these arrows are coming, you can see here. As I am applying the moment in the clockwise direction, this member is showing some resistance. So, the resistance will be in the anti-clockwise direction from the moment. So, from C, as it is clockwise, the resistance is like this and the moment is acting in the clockwise direction. As it is clockwise, this is also having clockwise. This is clockwise, this member is also having the clockwise movement. And this is clockwise and the member is having the clockwise movement at J towards D, at J towards C. In this way, they have mentioned. For their use, they have given J as the corner, so I am taking the J. The slopes, distribution, stiffness. These terms you need to remember. And then, if the couple or the clockwise movement is capital M which is being applied at O, we know it gets the distribution among the members which are being M1, M2, M3 as we have already mentioned. Okay. Now, the ratio of these in their proportion of stiffness. This is the distribution theorem. How the M1, M2, M3 will come? Those ratios will be equal to the same proportions like the stiffness of the members. So, M1 equal to M1 is to M2 is to M3 is to M4 is to M5. Ratio of all these 5 parameters and individual formulas. What is the moment formula? 4. These are the formulas for the stiffness. Moment proportions will be in the ratio of the stiffnesses. So, stiffness of the first segment, stiffness of the second segment. As we have taken our older example only. So for this members, what is the stiffness of the first segment? First segment will have 4 as it is being fixed, and it will have some Young's modulus, and it will have some moment of inertia and particular length. So this is the stiffness of the first member AO or OA, and for the second member 3 E2 I2 by N2, as the Young's modulus of each segment is different, as moment of inertia of each segment are different, and length of each segment is different, and support conditions were different. Showing all the variations, I have got the stiffnesses as sigma 1, sigma 2, sigma 3 and so on. Now I am taking the moment ratios, how the moment is getting distributed. As I already know, the moment distribution will be same proportion like the stiffness ratios. So all these moment ratios is equal to stiffness of the each member's ratio, and multiplying that we have got, and see here, only I am considering moment of inertias are being different and taking E as a common. Finally, I left with I1 divided by 4 and taking E same. All the members may be of a steel, may be of a concrete, maybe the joint is having same material. So I am cancelling E's in every segment. Okay, E cancelled, and then 4 is there. I am taking all the 4s to the down. So I1 by L1 is equal to 3 by 4 of I2 by L2, and 4 and 4 are getting cancelled, I3 by L3, and then 3 by 4 of I4 by L4, and then finally I5 by L5. What this term is giving? Ratio of the moments are being equal to or in the same proportion like the stiffnesses of the members. Now the ratios I1 by L1, 3 by 4th of I2 by L2, I3 by L3, 3 by 4th of I4 by L4 and I5 by L5. All these are called as relative stiffness of the members. So the relative stiffness is like this. Once the stiffness is calculated such as 4EI by L, and with reference to the next term I am giving, right? So the relative stiffnesses I can write like this. So the relative stiffnesses, these terms I can say. The first member is having I1 by L1 stiffness, and the second member may have 3/4 of I2 by L2. So that is the relative stiffness of the second member. Therefore, the relative stiffness of a member at a joint whose farther end is being fixed. Okay, relative stiffness value is equal to I by L. What is this I? I is the moment of inertia of the particular member whose I am calculating the stiffness, and L is length of the particular member. Okay, I is moment of inertia of the section and L is the length of the particular member. If the member is having farther end as the fixed end, the relative stiffness answer is, or the relative stiffness formula is I by L. If the farther end is hinged, the relative stiffness of the member when the farther end is being hinged, due to that condition 3/4 of I2 by L2 is the relative stiffness. So relative stiffness is having again two formulae. What are those relative stiffness formula? If farther end fixed, if the farther end is fixed, relative stiffness is equal to I by L, just the ratio of moment of inertia of the section by length of the section. Otherwise, in the next case, we have got farther end as hinged. Due to this condition, what is the relative stiffness? What is the relative stiffness means? 3/4 of I by L. Moment of inertia of the particular section, length of the particular member, that multiplied with 3 by 4 only will give the relative stiffness. Okay. So this is the relative stiffness term. So in the previous step, we have calculated using the stiffness of the members, or using this relative stiffnesses also we can calculate distribution factor. Using stiffnesses, how we have calculated? Stiffness of the particular member divided by stiffness of the total members at the joint. Okay, stiffness of the particular member by stiffness of the total members at the joint. that is one way of calculating distribution factor. Or we can use relative stiffness term also for calculating the distribution factor. That formula is equal to the distribution factor for a joint member using relative stiffness concept. Okay, that is equal to relative stiffness of the member divided by total stiffness at the joint. Same like this condition. Either distribution factor is equal to stiffness of the member by stiffness of all at the joint, right? Directly using the concept of stiffness, I can write distribution factor, or using the concept of relative stiffness also, I have taken next formula for distribution factor, that is relative stiffness of the member divided by total stiffness at the joint. This answer will be equal to the distribution factor at that particular member only. Okay. So in this way we have calculated this part. In the next class we will go into a numerical. There you can get enough clarity for calculating the relative stiffness also. Thank you.